Right, a bit more revision for AS and a bit of new perhaps. So starting off with a bit of revision here, it says find the Cartesian coordinates for the following. So at the moment they are r theta. So you need to change them into xy's. Then question 2, it's the reverse, they're xy coordinates. You've got to make them r theta coordinates. Try them by hand. If you need to, use your calculator. Remember turn it on. That's helpful. Oh, mine says low battery. Must have used it a lot. Right, menu, run mode. Time. And if you want to go to, I think it's options, F3 for complex, press the arrow, you get that change r theta to a plus ib buttons, and you can play there with those. If you ever need to put the angle button in, it's above shift x theta t button. Anyway, you have a play with that. And then question 3, find the Cartesian equation of the following polar curve. If you remember that, let me just draw a little diagram here. You have to use that fact. If you remember that, that's r, and now that coming down there is y, that coming along there is x. That's a 90 degree, and that's your theta. And then you can use the fact that x squared plus y squared equals r squared. And also, if you want to find any of these, like sine theta is opposite over hypotenuse. So you've got that fact that sine theta is equal to y over r. That might be useful for that. So I'll play with that. And then find the polar coordinates, question 4, for the following Cartesian. So it's replacing it the other way. So I'll pause this video now, have a bit of fun on your whiteboard that you've got from college, or maybe on a piece of paper, whichever one takes your fancy, or draw on the walls if parents allow that sort of thing. So please pause the video. And now it's unpaused. And here are the answers. Hope you got them. If you haven't, check back, have another go. Right, today's lesson, you should have the handout with you. I gave it you. Hopefully I gave it you anyway. And so today we got to know what is meant by an odd and even function, which you should have met in core maths, but maybe not, don't know. To be able to write a complex number in exponential form, to be able to convert an exponential form to Cartesian or polar form. So you can see here at the bottom, there's the polar form, and it sends an arrow too, so that implies this is the exponential form. But we shall see. Right, odd and even functions. Which is which? Hopefully you can see that's cos and that's sine. Which of these is even and why? Question for you. Cos x is the answer, and why? It's because it reflects itself in the y-axis. So what that actually means is that, say, like sine, cos say 35 will be equal to cos of minus 35. They're the same. Often comes in handy. Which of these is odd and why? Well, there's not much to choose from, is there really? It's sine x, because that's like the opposite. That rotates, doesn't it? But you can say that like sine 35 is equal to the negative of sine negative 35. Let's look at that on the diagram here. So if I was looking at 35 degrees, and if you were looking at 35 degrees, and it's in radians, I don't know what that is. It's less than 5 by 2 anyway. So you might be looking at that value there. Well, we're saying, oh, get off. It's the same as that value there, the negative of it, because it would be putting it up there. Yeah. So that's an odd function. Right, proof of the polar form. Here we go. So a good friend you met last year. Further maths people can have friends, but not many. A good friend that we met in the formula booklet was Maclaurin's series. I'll spell it wrong now. I'll have to look at my sheet. No, that's got no, I'm wrong already. Maclaurin series expressions. Here we've seen these from Maclaurin. Oh, good. Right, now we're going to prove the exponential form with them. So here we go. It can be proved the series expansion of e to the x is also true if x is replaced by a complex number. If you replace x by I theta in the series becomes, so I'm just putting I theta over here next here. So we've got I theta. Then we'll have plus I theta squared. Oh, I'll write it and then we can change it. Over 2 factorial plus I theta cubed over 3 factorial plus I theta forward over, oh, before the 4 there, 4 over 4 factorial. How many do I have to do to make sure this up? Oh, 6. Gosh, we're going for it today. Plus I theta 5 over 5 factorial plus I theta power 6 over 6 factorial. Whoosh. Right, so this one's just I theta. This one becomes minus theta squared over 2 factorial. This becomes minus I theta cubed over 3 factorial plus theta 4 over 4 factorial plus I theta 5 over 5 factorial, my head's in the way, minus theta 6 over 6 factorial. Now do we see anything? Hopefully you do. Is that the highlighter? Oh dear. Hopefully you saw anything. I can't go backwards now. Bother. You should have seen that the real bits were in fact the cos formula and the I bits were the sine formula, but with the I in front of it. It made it a bit clearer here. So it's just what we had before. Those were the real bits of it and those were the I bits. But you should be able to see that that's the sine Maclaurins and that's the cos Maclaurins. So in fact what we've got here is cos theta plus I sine theta. So that is that. So we can write in polar form, we've just got an R in front of it, haven't we? So that's R cos theta. So we can just replace that cos plus I sine theta with e to the I theta. So we write z equals R bracket, if you like, or not like, e to the I theta. And that's the exponential form from polar to exponential. Easy to see with Maclaurin. Super. Yeah. Right, to multiply complex numbers in polar form, we multiply the moduluses and we of each complex number together and the arguments. There's that formula for that. To divide complex numbers, we divide the moduli and we subtract the arguments. There it goes. So exponential, very similar. It's that, add the args times the r's, divide the r's, subtract the args. Sorry, divide the r's, yeah, subtract the args on the other one. Yeah, lovely. Proof of the timesing formula. Now, scary bit of core maths there that you may or may not have done. The addition formulas, they come in the formula booklet. You are going to learn about them in normal maths, so I shall leave that to your teacher. We're just going to use them. Right, so proof. Oh dear, we're going to have to multiply all this business out. So we've got R1, R2, big bracket, and if we do this, we'll have right small cos. No, it's not cos. Cos theta 1, cos theta 2, plus cos theta 1 sine theta 2. I've got an I in front of that one. Plus, and then it's I sine theta 1 cos theta 1, and then subtract sine theta 1 sine theta 2. So we want to put the real and the imaginary together, I wonder. Yep, let's do that. R1, R2. So big bracket, what have we got? It's real. We've got cos theta 1, cos theta 2, take sine theta 1, sine theta 2, and then we've got plus I, and open another bracket. And we've got cos theta 1 sine theta 2 plus sine theta 1 cos theta 2. Right, so using the addition law, looking at these, that one looks like the real, doesn't it? So we can replace, right there or above it. Okay, right there, I think. So we're going to put that first bit is the same as cos A plus B, so that's cos theta 1 plus theta 2. And then the second one's like the one on the bottom, isn't it? So plus I sine theta 1 plus theta 2. See, that's really shown the proof for that, because you're adding the arcs times in the mods. Division 1 can be proved as well if you were interested, but you have to do a bit of rationalising the denominator when you do that one. So I'll leave you to play with that perhaps at home where you are. If you want to pause and have a go. If you don't, well, never mind. Let's have a move on. So express this in not polar form, in exponential form. Okie doke. So you could draw out, if you wanted to, draw out the thing we've got here, 2 along, 3 down, join them up. So the angle it makes with the positive x-axis is that. That's our theta, and the r is the length of that, which is done by a bit of Pythagoras, isn't it? So that's 2 squared plus 3 squared. Oops, what are we doing with the I? You don't need that. And then root u. So that's 4 plus 9, 13, root 13. The theta, tan to the minus 1 of b over a, keeping all negatives out of it. And if we do that on the machine, that comes out at 0.983 in radians, which is what it wants. Because we can clearly see that theta is a negative from that, because we want to make it all correct. Oh, yeah, a negative there and negative there. Right, now we don't. So the form is r is root 13, and it's e to the, I'll put the number first, 0.983i. And that's in our what's it for? Next one. Just having a look on the calculator. Does it have the exponential form on? No, if you just get r and theta, you just know what you're doing, don't you? Right, this one, express blah in RE to theta. So this first one's dead easy because we can see R is root 2. And we can see theta is pi over 10. It's in polar form. Done. The second one, unfortunately not in polar form because there's a minus there. If you remember what to do, you have to write that as, hopefully you're getting it. It's the same as that. Now it's in true polar form, and therefore you can write it as 5 e to the minus pi by 8i. Done. Right, on your whiteboard, have a go at these. Oops, put a bit of the answer up there. Have a go at that one. Here's the answer. Then have a go at that one. Drawing them out is important, or if you're cheating and putting them in the calculator, I can't stop you. But knowing to do it by hand is obviously very useful. When you get to uni and you're doing maths, they don't let you have some calculators, so you need to be able to do it. That's it. I'm adding the answer. It actually says, let's put it here, it's 2 e to the minus, I can't read it properly, yeah, minus, it must be minus 2 pi over 3i. And that's said 2. Now you're going to want those two answers, so jot them down if you've not already jotted them down. We need them for the next part. So make sure you've got the two answers written down, because it's going to ask you to multiply them together, I think. No, it's divide first. If you divided those two complex numbers together, what would you do with your two answers? Write it down, remember the shortcut. So that's the answer. Now you're multiplying them. I'll just give you a minute while I go and turn my stove down. Okay, we should have done that. And I'm adding the answer. But it says 4 root 2 e to the minus pi by 5. Pi over 12 pi. No, it's that thing. 12 pi over, no, I can't even say it. 5 pi over 12. Right, what now? Express this thing in a plus ib. Well, It's quite easy if you're using machine, just put it in your machine, I think. You can enter that straight in. Why do you want to do this? I don't know, because if you enter that straight in, root 2 e to the power 3 shift pi shift I ABC4. You just enter it in, it gives you the answer on your calculator straight away, so not much point in it. But never mind, didn't have a calculator, just quickly, I would do it. That's root 2, that's that over that. So I write it in polar form. No point to this because you're actually going to stick it in your calculator anyway. Or you might know these things if you might know what 3 pi by 4 is as an angle. You may know your angles well. That's -1. They're quite well known ones, but nowadays people don't remember them. I think when I went to school we had to remember them. I don't remember them anymore. And then when you times by root 2, you just get what your calculator said anyway, -1 plus I. Done. We can just plug it in, so I won't bother, unless you have to. This one, express this one in the form r cos theta plus I sin theta. Oh, well, you think that were easy. But that is not in the range of what we call the principal argument, which is at minus pi to pi, which is over there. So how do we get it in that form? Well, we keep taking 2 pi from it to get it in the right place, because basically, if we were to draw that thing, remember that going round, that's pi, that's 2 pi. So that would be, what would that be? That would be 5 fives, 10 fives, 15 fives, 20 fives, and then we've got another 3. So 3 over 5 would be sticking out somewhere up there, wouldn't it? So all we're doing to find that angle, that's what we're doing, trying to find that, that's the angle we want. So you can see it's now just 3 pi by 5. But to get it in that range, to keep taking 2 pi from it until it gets in the right range, and then it gives you a number. If you took 2 pi from that, that would be 13 pi over 5. Say not in range, take another 2 pi off it, and you get 3 pi by 5, which is in range. So that's the one we want. So therefore Z would be 2 cos 3 pi by 5 plus I sine 3 pi by 5. Done. Yeah, that's what that's going over there. Right, use this thing to show this thing. Oh, it's a bit more exciting. We do need to be doing this. So we can use this fact. We can also think, what's this? What would that be? That might be useful. Well, that would be cos of minus theta plus I sine of minus theta. And you know that that is, in fact, what we've got written down there, because the cos is an even function, the sine is an odd. Right, in the formula up the top there in the question, they're adding these two things together. So if we were to add them together, what would we get? Basically that one and that one. Well, adding them together, the I signs disappear. So we're just left with 2 cos theta. So now that implies what we've got above, doesn't it? That cos theta is a half of e to the I theta plus e to the minus I theta, which should now remind you a little bit of cos that you met last year. Didn't have i's in it though. You can get a similar one for sine theta. which will remind you a little bit of shine, perhaps. Right, on your whiteboard, I think now. Expressing the form A plus IB, I'll just put in your calculator and write it down, or do it like we showed you, read off the R, read off the theta, and then stick it in the other formula, polar formula. What says without a calculator, little sneak. So you should know, basically saying, do you know what cos of 2 pi by 3 is? Bet Seb does. Do you know what sine 2 pi by 3 is? If you don't, you'll have to cheat with your calculator, but other people too. Mark should know. If you're thinking of going to Oxford or Cambridge, they'll expect you to know these things. Anybody else that's not taking it away from anybody else, there might be somebody else out there that knows them all. Anyway, here we go. You might put it just in machine if you don't. Gives you that. And this one over here, have a go at that one. And there we have it. Okay, so I bet there's a worksheet. Yeah, it says a matching puzzle. Yay! And then a worksheet. You can't do the puzzle though because you're not here. And I don't think it's fast to give you the puzzle to expect you to put it out and have a go. So we'll miss out the puzzle and just do the worksheet. But there is a little challenge here for anybody who needs it. And anybody going to any of these top Russell universities might want to have a go. If you're not, I'd just leave it and get on with the worksheet and stop the video now. However, if you like a challenge, or you need a challenge, here we go. It says, without integrating by parts, which you've not learned how to do yet anyway, can you find the integral of this thing here? There's a little hint. Only little. Oh, I can't go backwards. Oh, bother. The hint. What was the hint? I can't remember now. I think the hint was, I've spoiled it now. Oh, idiot. The hint was, I think it was that sine. I think it's going to pop up on top of the screen, but I don't know when. Do one more. That's the hint. Yeah, that was the hint. So you're integrating this thing, and that's your hint. Which one doesn't help, so I'll give you a next hint, which is equal to that. I think you need that hint too. So basically, you're replacing sine theta with imaginary e to the I theta. So I'll just write that down there, give you that bit. That's what you're replacing. You're trying to integrate that. Just give you a minute or two, see what you make of it. It's quite hard. And you can just do this if you're wondering. Another line, because it's hard. That's meant to be helpful hint. Basically, it's trying to say to you here, if you had an imaginary of 6 plus 4i, you could take out a factor of 2 and write it like that. So here we're going to take out a factor of, it might not be useful for this. I don't think that's very useful. That must be useful somewhere else. Sorry. Right, this thing, write it like that. If you've learned how to integrate E, it stays the same, but you divide by the new power. So basically, you get that. Next step, it doesn't actually write it, but I'm going to write it. We can write that as, ooh, get off, E to the 1, E to theta, E to the 1, I'm not expanding this, over 1 plus I, E to the I theta. And then it replaces E to the I theta with cos plus I sine theta. Keep stopping me, pausing the video if you're having a go and don't want to listen to me. So it replaces E to the I theta with that. Then if you now get, oh no it doesn't. Oh. Oh, putting the limits, that's what it's done. I'm wondering what it's up to. If you put the limits in, if you put cos theta plus, sorry, cos pi plus I sine pi. Now if you cos pi, what do you get? You get 1, do you? Oh dear, remember again, not mean to use me. Cos 180. I don't know why I'm doing this, I should know. Oh, it gives you -1. And if you use sine pi, that must be 0. And then if you put the noughts in, you get a 1 and a 0 again, don't you? So basically, it ends up giving you that if you've done it. So let's put the limits in. Then we've got rid of rationalised denominator. Gives that. Pull the imaginary bits out of that. And we get that final answer that I've now scribbled all over. So I shall rub it out if I don't mess it up. About that extra step I put in. There you are, and there's the answer. Maybe you got it, maybe you didn't. So anyway, I think that's a bye-bye from me. Enjoy the rest of the day, and I'll see you back in class. I think that's the last of our online lessons for, hopefully, unless we go backwards with the COVID. So see you in class.